does the sequence an equal to 2 to the negative n satisfy the conditions of the monotone convergence theorem? Does the limit of the sequence exist? Okay. So if it does satisfy the monotone convergence theorem, then yes, because the conclusion of that theorem is that the limit exists. Okay. But it's entirely possible that maybe it doesn't satisfy the monotone convergence theorem, but the limit still exists. That can happen. Okay, so let's talk about this. What do we need for the monotone convergence theorem? Okay, so monotone convergence theorem says if your sequence is bounded and monotone, so remember monotone either means increasing, strictly increasing, or decreasing, or even strictly decreasing, then the limit as n tends to infinity of the ANs exists. So that's the monotone convergence theorem. We're just being asked, does it satisfy it? So is this sequence bounded and is it monotone? Okay, we've got AN 2 to the negative n, but that's just 1 over 2 to the n. Okay, so that's our sequence. We're not being told a starting index. It actually doesn't matter here. Although usually if no one tells you where you're starting, you assume that n is 1 or sometimes 0. Okay? But we can actually show bounded and monotone without knowing exactly where we start. Okay? So notice that this sequence, I'm just going to, as an illustration, assume that it starts with a 1. This sequence looks like 1/2, 1/4, 1/8, 1/16. These are decreasing. They're heading towards 0, but they're staying positive, but they are decreasing. Okay? So we might want to show that. Okay? Actually show that this sequence is decreasing, because then it would be monotone. Okay? So, satisfy the conditions of monotone convergence theorem. That's all we need to do. Just making sure I got the right limit there. Or not right limit, right sequence. Okay. So, we propose, we'll be all fancy about this, we propose that our sequence is decreasing. Now you can say strictly decreasing, I don't particularly care. Okay? So here's what I'm going to do. I'm actually going to show, so what do I need? What do I want to show? I want to show that the next term, an plus 1, is less than or equal to, but we know it will be less than, the current term, an. How do we actually establish an inequality like that? Well, we suppose, well, I would not say we suppose, we know for any n that n is less than or equal to n plus 1. Okay. Now, since 2 to the x is an increasing function, we can see that 2 to the n is less than or equal to 2 to the n plus 1. Now, both of these are positive. Now, why do I care if they're both positive? Well, an inequality like a less than or equal to b can transform into a 1 over b is less than or equal, I've got it wrong, less than or equal to 1 over a by reciprocaling things, but only if a and b are the same sign. Either they're both positive or they're both negative. Well, what have we got? 2 to the n is less than or equal to 2 to the n plus 1. So it follows that 1 over 2 to the n plus 1 is less than or equal to 1 over 2 to the n. Okay, but that's just 2 to the negative n plus 1 is less than or equal to 2 to the negative n. But this one is the next term in our sequence, an plus 1, and this is an. So the ANs are decreasing. Or if you wanted to, you could say non-increasing. Sometimes people think decreasing has to be strictly decreasing. Okay. So I'll just say non-increasing. But that does mean that it's monotone, because it's all heading in the same direction. That's great. That's one of the conditions we need to show. Okay. So since the sequence is decreasing, we can see its first term, which I will assume is A1 because no one said otherwise, is an upper bound. What do I mean by that? A1 is greater than or equal to AN for all n. Okay, it's the biggest the sequence can get. Okay, so that's sort of an upper limit, a ceiling. We cannot go further than this. Okay. Let's say, notice also that AN is a power of 2 and therefore is positive. So AN is greater, I'm just going to write greater than or equal to 0 for all n. So our sequence is decreasing, and we can see that every term in our sequence is, the smallest it could possibly be is 0, and in fact it doesn't even reach that. The biggest it can possibly be is AN, or is A1. Okay. So the sequence is bounded. Okay. So what do we need for the monotone convergence theorem? You need bounded. Got it. You need monotone. In this case, it's non-increasing. Got it. So yes, this particular sequence satisfies the conditions of the monotone convergence theorem, and its limit exists. Now, let's double check the question again. Does the limit of the sequence exist? Okay, so that's it. We're done. Yes, the sequence has its own limit. We could point out the limit is 0. No one asked for that, but we could go ahead and say that. So we'll just write that off to the side. Okay. So we had to go through this. I find when it comes to doing monotone convergence theorem, the monotone really lends itself to being bounded. Because as soon as we knew that the sequence was decreasing, the very first term has to be the biggest it ever got, because it's only going to decrease from then on. And then you really just need to show a lower bound. Or if it's increasing, everything's flipped around. Okay? So monotone's probably the best one to go for first when trying to establish the monotone convergence theorem.